Hi, it's time for another math easy solution. Time to discuss further into applications of integrals and now look at further into hydrostatic pressure and force and go over example 2 of the example series. So yeah, make sure to watch my earlier videos on the introduction and the example 1 on hydrostatic pressure and force to get a more detailed idea of it. So now this example we're going to solve as states: find the hydrostatic force on one end of a cylindrical drum with radius 3 feet if the drum is submerged in water 10 feet deep. So it's in water. We're dealing with US customary or US imperial units, feet. So let's just deal with that instead of the SI units. So if this is the water level, and let's draw let's say the bottom of this this water, whatever it is, water depth, and then we have a drum, or just a circular drum. We'll just shade it in like this. So we want the force on one side or one end of it. So on this point, what's the force all applying on it? And the radius here, if this is the center, radius is going to be 3 feet, and the full depth is 10 feet. So that's what we have right there. So now let's look at the solution to this example. Well, basically the first thing we should do in this example, it is convenient to choose the axis so that the origin is placed at the center of the drum. And the reason is because it's a circle, so once the origin at the center, we could write a simple equation for that circle, and we'll get to that in a bit. So let's just draw these out. So let's say that the circle is, let's say we have this xy axis. This is the x. This is the y. Just draw it vertical like that. So it's at the center of this drum, which is a circle. So we have that, and then the negative part of the y-axis goes down, and this is the left side like that. So if this is the drum at this height right here, it's a radius of 3, so that's 3. This is the origin 0. At this point is negative 3. And at the water height right here, or the full water depth, this is 7. That's because the bottom of the depth is here is 10. So 7 plus 3, or yeah, so 7 plus 3 is equal to the full 10. Let's draw it like this across there. And what we get here is this equation for this circle is just a basic circle. X plus y squared equals radius squared, where in our case our radius is 3 squared, which equals to 9. So 3 squared is 9. Yeah, and here I've basically written that part here. Then the circle's simple equation, x squared plus y squared equals 9, and you could learn more about the equation of a circle in my earlier video, and I'll put that in video links below. So as an example 1, we basically divide the circular region into horizontal strips of equal width, and then we would obviously sum it up to infinity and get an integral. So again, make sure to watch example 1, which is really useful on that. So what we'll do here is, so if we take a horizontal strip, let's just go like this, like that, and at this point here, this point, this we'll call this y. This is yi, that's yi strip. The bottom here, this is just yi minus 1. And then at this point inside, is this any point inside here? This point right here, we'll call this yi star. Where again, from example 1, yi star is similar to the xi star. This is just an element, or it just means it's any number inside the interval yi and yi minus 1. So the reason we're doing this is just means element of any real number inside here. That's what this e symbol, this thing is a Greek letter for, that's what it just means. So it's just yi is any value in between these two, and the reason we're doing this any value is because that's the value at that's on the circle. That's the y value at the circle, and then the x value here, if we draw it, let's say like this. So this x value here is going to be, we'll call this xi star. And this is important again from my integration videos. When we take this infinitely small, this yi star is going to be, it's going to coincide with yi and yi minus 1, because when it's really, really small, it's pretty much the exact same numbers as all those, and then we could use just the number y, just the value y instead of yi star, and we'll get to that later on. So we divide these again into equal width. So this is just one of the subsections, so we'll call this delta y. So that's an equal width. We're going to have, let's say, 4 or 5 here, but we're going to obviously have infinitely many of them, all infinitely small. And now from the equation of a circle, we can see that the length of the ith strip, I'll just draw this like here. I'll draw this in red again, actually. So this length right here, all the way down here, we'll call this Li. And we can solve this because this Li is just equal to, well, 2 times this xi star. So we could write Li for that ith strip is equal to 2 times xi star, and then we could solve xi star from the equation of a circle, just solve for x. So we have x squared plus y squared equals to 9. So x is going to be equal to, just move this over, 9 minus y squared, and all square root plus or minus like that. But we're only going to be dealing with the right side here, the positive x value. So we'll only deal with the positive side. And then, so what we get now is xi star equals to positive. Then we just plug in the yi star there, minus yi star squared. And then we could basically throw this inside to get Li. Li is equal to 2 times xi star, which equals to 2 times 9 minus yi star squared. And we're going to write everything in terms of yi star, and you'll see why later, because again, we're dealing with the vertical axis there, where we're doing the strips where the delta y. And now, like I explained in my earlier video, the pressure on this strip is approximately, we'll just call this Pi, and this equals to, like I showed in the introduction video, this is going to be equal to the weight density, or this is delta times by the depth di. And again, where the di, that's the depth of the strip. So in this case, we'll look at it at the center point, at this point here, yi star. And now this is our depth here, because the pressure change increases with depth. So this is our di right here, and we know what this di value is because, well, this height right here is just yi star. So the di, the full height, and also we know that this full height across here is 7. So the di is going to be, we could write it in terms of yi star. Di is equal to 7 minus yi star. I'll just circle this. So that's what our di is going to be equal to. And also now our delta, this is like I explained before, this is the, I'll just write delta equals to the weight density. Okay, and this is weight density, and for water we have delta water in US customer units is 62.5 pounds per foot cubed. So now we can just plug this inside, and since we're just using, it's going to be in feet, we're going to be dealing with pressure in the units of pounds per foot squared, because once you multiply this is in feet as well. So let's just plug this inside, just ignore the units because units are we're all dealing with feet or pounds per foot cube. So now we have 62.5 times by 7 minus, this is di, this is yi star, which yi star is also in feet. So yes, so also recall from the introduction video on pressure and force for hydrostatic pressure and force, that the pressure is the pressure is just force per unit area. So the total force on the strip, and this pressure is at all directions, so the entire depth di, that's the pressure. So we want to find the total force across the entire strip, so we would just multiply this force n is approximately by, just multiply by the area. So pi times it by ai of the strip. And again, that strip right here has an area that's just going to be, well, look at it, that's just Li times delta y. So this equals 2, and then this is delta times di, and then this is going to be times Li times by delta y. That's the area of that horizontal strip. So let's plug in what we do know. Again, we know all these values is 62.5 pounds per foot cubed, times it by di, which is 7 minus, that's just this above, yi star, times by Li, which is 2 times 9 minus yi star squared. And that is just our length right here. And then times by delta y. So we have everything in terms of yi star and delta y. And now, as I show in example 1, the total force is simply obtained by adding the forces on all the strips and taking the limit as you have a number of strips goes to infinity and they're all infinitely small. So the total force F is going to be equal to, well, the limit as n approaches infinity of the summation, and now you're going to have infinite strips with the force Fi, I equals 1 up to n. And this is our Fi, we could plug that inside. So it goes limit, n approaches infinity, and then this is n, this is I equals to 1. Plug this stuff inside. 62.5 times it by 7 minus yi star, times by 2, times by square root 9 minus yi star squared and delta y. So we have all this together, and now this is by definition a Raymond's sum, and it equals to an integral. And again, make sure to watch my earlier videos on integrals and its derivation. This is pretty much it. So this equals to, let's take the constant value out. So 62.5 multiplied by 2, or constant, take the integral, now it's from -3 to 3, because that's how we set up our axis. And now we have 7 minus y. Again, when delta y is infinitely small, the yi star coincide with yi and yi minus 1, which is just y. So it is pretty much all one value, we'll call it y. And then we have our integral, 9 minus, again, yi star as well, y squared. And then the delta y is infinitely small, so dy. And there is our integral right here. Let's just simplify this further. Let's just multiply 62.5 times by 2. That just equals to, well, I just want to do this just for fun's sake. So 60 plus 2.5 times 2 is a quick way of thinking about it. This just equals 2. 60 is 120 plus 2.5 times 2 is 5, which equals to 125. Okay, so we have that part set up. So we have F is equal to 125, and then we can multiply these out, expand that out. Integral from -3 to 3, we have 7 times square root 9 minus y squared, and then minus, so this is all square bracket, minus, then we have y square root 9 minus y squared dy. And then we could write this as two integrals right here. So we have 125 times by 7, integral from -3 to 3. And this is 9 minus y squared dy. Then minus, we could multiply this inside. Yeah, minus 125, that multiplied inside, times it by integral from -3 to 3 of y, and then this is 9 minus y squared dy, like that. So we have two integrals right here. We have 1 and we have 2 right here. And we're going to solve these separately and also show you some pretty useful tips in solving this. For the first one, again, this is in the form of trigonometric substitution, so we can use trig substitution like I went over in my earlier videos. Substitution, and use basically y equals to 3 sine squared theta. I mean, it's 3 sine theta. Then when you could plug this inside, you could use a trig identity to simplify it. But what we could also do is notice that it's easier to basically notice this is a semicircle. This is, yeah, I'll write, but it is easier to notice, that it is you have to notice it is a semicircle, and we can use the equation of a circle to solve it. Semicircle. So, and again, to do that, well, we have this function here. It's in terms of y, so we have, so let's write this integral right here. Integral -3 to 3, and I'll write that one, yeah, I'll just write that down. So now we have 9 minus y squared dy. So this is in terms of y, so we have, let's say, x equals 2 square root 9 minus y squared. And again, you know, if you evaluate this one here, this is just square both sides. X squared equals 2 9 minus y squared. Move this over, again, it's just a circle. Equals 9. It's a circle except x is positive here. So x is greater than or equal to 0. Because, yeah, you can't have a negative value with a square root, a negative real value. So it's positive, so it's a semicircle. And again, let's just graph this out. This is x, this is y. And then at this point here, at y is equal to plus or minus, let's go 3 right there. So it's radius of 3. Plus or minus 3, we get x equals 2, 9 minus plus or minus 3 squared, where we get, well, basically that's equals to square root 9 minus 9 equals to 0. So we know that the semicircle just looks like this. And it's always positive and then when y is 0, this is just square root 9, which is 3. So this is 3 right there. So it's a radius of 3, so let's write that here. At y equals to 0, we have x equals 2 square root 9 minus 0 squared is equals to square root 9 equals to 3. And then all the radius is here, 3, -3 for y, and again it's a semicircle. So the area, is just equal to pi r squared divided by 2. That's the equation of a circle. Then divide by 2, so equals to pi times 3 squared divided by 2 equals pi 9, yeah, divided by 2. And this area is equal to, it's basically the integral. So this is the same thing as area there. So we've solved it, so thus the integral from -3 to 3 of square root 9 minus y squared dy is equal to pi times 9 over 2. I'll also put that in front, 9 over 2 pi. So we've gotten this first one there. Let's look at the second integral right here. Integral -3 to 3 of times by y square root 9 minus y squared dy. This one we could also simplify this. So the integral from -3 to 3 of y 9 minus y squared dy. So notice how that the interval is going from -3 to 3, so it crosses y equals 0. So what we could do is notice that if x equals to y 9 minus y squared, then what we have is, then let's just say this is x is a function of y. So x of y, let's just say we put a negative y value. So when we put x of negative y, we get negative y 9 minus negative y squared. Because of the squared value, we end up getting negative y, and then 9 minus y squared, which is basically negative x of y. So we have x of negative y is equal to negative x of y, and again, like I showed in my earlier video on symmetry of functions, this is an odd function. So this means that it's symmetric about the xy axis, in this case about the y-axis, except it's flipped to the bottom half. So for example, of one, recall, if you have an odd function, so this is, let's say x, that's y, and then just a random one like that, and this is at a, call this f of x. So if this is exactly reflected, and then, so this is an odd function, so f of x is equal to negative f of negative x, and this is at negative a, so this areas cancel out. And again, like I showed before, my properties of definite integrals, the integral from negative a to a of f of x is equal to 0 if f of x is odd. So if it's an odd function, it's 0. So in our case, since I just showed that it's odd, this function is an odd function, then the integral is going to goes to 0. Thus, integral negative 3 to 3 of y square root 9 minus y squared dy is equal to 0, and we don't need to actually solve it because we know it's odd. So that goes to 0. All we're left with is 9 over 2 pi, and obviously times the constant 125 times 7. So this goes to 0, and this goes to 9 over 2 pi. So we could plug it in all together. So now what we have is our force is equal to 125 times it by 7, and then times it by, this is times it by 9 over 2 pi. And now if we plug into our calculator right here, I'll just type in the top part so we have an exact value. It's simplified. 125 times 7 times 9 is 7875. So this equals to 7875 divided by 2 pi. So that's our exact value. And now when we solve this, let's just solve this divided by 2 times it by pi. And we get finally 1237 0.02, or I'll just write this as approximately equal to 12370, and the units are pounds. So thus F is equal to roughly 12,370 pounds, and the units was pounds because we had the weight density in that was in pounds per foot cubed, and everything else was in feet, and then basically they just cancel. We end up getting pounds. So anyways, that's all for today. Hopefully you learned from this pretty useful, interesting example, not only physics and engineering in terms of hydrostatic pressure and force, but also how to solve integrals by using these simple tricks such as symmetry and realizing that the shape is a circle or a semicircle, and then just applying the formulas to that. And also the odd function, you can just cancel and make it 0. Anyways, that's all for today. Hopefully you learned, and like always, you can download these exact notes in the link below. Thanks for watching, and stay tuned for another Math